Well, can you guys hear me?
Okay, yes. Hi, George. How are you?
Good. Would you like me to introduce
Sure,
Dr.
go ahead. Yeah, I was just about to do that. It's 1:05. Please go ahead. I have in front of me, but please go ahead. I guess that's more appropriate.
All right. Well, thank you very much. Welcome, Dr. Shi. It's my pleasure to welcome Dr. Li Shi from McMaster University to our seminar series. Dr. Shi is an associate professor of chemical engineering at McMaster in Canada, where he specializes in the numeric simulation and modeling of complex fluids, materials, and flow systems such as dilute polymer solutions and such. He obtained his PhD from the University of Wisconsin-Madison and completed his postdoc training at MIT. Dr. Shi is particularly interested in sustainable production of polymer materials, dynamics of turbulent flows, the rheology of polymer melts, and the structure-property relationship of polymer materials. So without further ado, I'll leave the floor to Dr. Shi.
Thank you, George, and thank you, Hossein, for the invitation and for hosting the seminar. I really appreciate the opportunity to share the research in my group with the audience at Toledo. As you may remember, that the seminar was originally scheduled in February, but we had a snow day. I hope it wasn't too bad back then. So now I have to give up all the February jokes I prepared. Now we are in March. So happy March, everyone. The topic I'm going to discuss today is on turbulent flow, which is a topic that I hold very dear to myself. But unfortunately, there are fewer and fewer people in chemical engineering, that's in my home area in chemical engineering, that still work on turbulence. So very often I find more at home when I'm talking with the mechanical engineering group. And I remember that when I was starting my graduate school, that was how long ago? That was 18 years ago, and my supervisor was proposing this project to me, and he told me that turbulence was one of the very last unsolved problems in classical physics. And as a first-year graduate student, like all first-year graduate students who are now sitting in the audience, you know that you're fearless. So I was like, okay, I'm going to take on it and I'm going to solve that problem. Now 18 years on, and I'm still here. We still have a lot of questions that we don't understand. We are making baby steps forward, hopefully. And I'm very glad that I have this opportunity to share of some of the small steps we are making towards the understanding of these fascinating phenomena. So let me just start with something that I think all engineering students would appreciate. This is I'm sure that everyone who had an undergraduate degree in engineering has seen at least some version of these diagrams or these experiments. Right, this is the famous Reynolds experiment, and we know that, let's say if you have a pipe flow, so we have a pipe flow, the fluid is moving from left to right, and when keep the flow rate low, we know that we have a laminar flow. That means that if you inject a dye, the dye will basically follow a straight line. That basically means that the fluid is moving in a very highly stratified manner, moving in layer by layer manner. But as you increase the flow rate, then you can see that the pattern will become more and more disordered until you have a fully turbulent flow. We know that this transition will be governed by one non-dimensional number called the Reynolds number, which, roughly speaking, it measures how strong the inertial force is compared with the viscous force. So the inertial force will try to destabilize the flow. It will try to trigger turbulence. Whereas the viscous force is trying to stabilize the flow and will try to make it calm down to a laminar flow. And when Reynolds number is high, the inertial force will win the competition, and you will end up with a turbulent flow. And most of us are familiar with turbulent flow, turbulent behavior of what we call Newtonian fluid or viscous fluid, and such as water. That's most studied. We are interested in viscoelastic fluids. So by looking at the word viscoelastic, we know that it's basically a combination between two words, right? Viscous and elastic. So we know where the viscous part comes from. It's a liquid. So there must be some viscosity of the liquid, right? So what do we mean by elastic? So I happen to have a rubber band here on my desk. So basically, when we talk about elasticity, we're basically talking about that the material have some sort of memory of itself. So let's say I have this rubber band, and right, without any force at equivalent, so it has a certain length. It's equivalent length, it's equivalent shape. Then I apply for a force. I can stretch the material, so it becomes longer, it becomes elongated, right? But if I relieve the deformation, I want to make sure I don't snap my finger. It's a little scary here. If I release my deformation, release of force, it will go back to its equivalent configuration. So an elastic material is something that has a memory. It remembers its old configuration. It remembers its old shape. And whenever you remove the external deformation, it will try to come back. And we make a fluid viscoelastic. Sorry about that. We make the fluid viscoelastic by basically dissolving some polymers into the fluid. So we're dealing with polymer solution here. At the equivalent, the polymers will coil up into a bigger big blob. And once you have a shear in the flow, the shear motion will try to stretch the polymer, just like when I stretch my elastic band, rubber band here. But after you remove shear, after you remove shear, the polymer will remember its old configuration, so it will relax back to its coil configuration, right? And if the flow is steady, if you have steady shear, there's really not too much thing happening here. It's pretty boring. The polymer will stay in this stretched configuration. The thing is that if you don't have a steady flow, if you have a turbulent flow, we know that in turbulent flow, everything is time dependent. We have fluctuations everywhere. The shear is changing all the time. So the polymer chain will keep on seeing strong shear, weak shear, strong flow, weak flow, and they are constantly changing in time. And you can imagine that this constant changing flow condition versus the relaxation dynamics, they will couple together and give you a bunch of very interesting nonlinear phenomena. And these phenomena can be measured by another non-dimensional group called Weissenberg number. It's defined as the ratio between the relaxation time, how much time does it take for the polymer to relax, to the time scale of the flow shear. So that's basically inverse of shear rate. So when the Weissenberg number is low, that basically means that compared with how fast your shear flow, the polymer is relaxing faster. So each time you try to deform the polymer, it will quickly find its way to go back to its original configuration. So there's not much interesting happening. The fluid will behave similar to a viscous fluid. But when the Weissenberg number is high, the polymer will take a long time to go back to its original configuration. That basically means that it gives you more chance for the polymer stress to couple with the complex flow motion to give you a bunch of interesting nonlinear elastic behaviors. So now let's look at compare with the Newton viscous fluid. We only look at the axis of a Reynolds number, right? So we have a laminar flow at a low Reynolds number. We have a turbulent flow at high Reynolds number, right? And we know that there's a critical transition for pipe flow that's happening at a major number of about 2100. Now when we introduce polymers into fluid, we basically have another axis here that's Weissenberg number, and we need to look at flow behavior in this Reynolds number versus Weissenberg number space. So there's a lot of questions about what happens in this corner. So that is what we are interested in. So we are specifically interested in the turbulent flow of a highly viscoelastic fluid, turbulent flow of basically the flow of both high Reynolds number and high Weissenberg number. And the phenomena has been studied for a really long time, back to the time of World War II, because of a phenomenon called the turbulent drag reduction. So we all know that if you have turbulent flow, the friction of a turbulent flow is higher than that a laminar flow. Basically means that if you have a same pressure gradient, so if you have a same pressure gradient, same driving force of the flow, in a laminar flow you're going to get a much higher flow rate. So this is a laminar flow you'll get, right? You get a much higher flow rate in a laminar flow compared with what you would get from the turbulent flow, because turbulent flow has higher friction. But if you dissolve polymers into the fluid, so you look at polymeric fluids, so you have polymeric turbulent flow, you can see that you can have a higher flow rate compared with, still lower than laminar flow. It is still lower than laminar flow, but compared with a Newtonian turbulence, you have a higher flow rate. So you have lower friction when we introduce polymers. This is called turbulent drag reduction phenomena, and in some cases you can get drag reduction. So the amount of friction drag reduction you can get can be up to 80%. So that's a lot of energy saving in fluid transportation. And ever since I moved to Canada, I thought to add a slide about fracking as well. Drag reducing polymers has been widely used as part of the ingredients in the fracking fluids to improve oil recovery efficiency as well. So the phenomenon has attracted a lot of attention ever since 70 years ago, and And what we learned later on is that as you make the fluid more and more elastic, as you either increase polymer concentration or as you increase polymer as you increase the Weissenberg number, it's not a single dry adduction phenomenon, but there's a very rich group of different behaviors that will happen. So let me just, before I move on to our more deeper insight into the phenomena, let's just look at the phenomenology here. What was observed in experiments? So what we are looking at in this diagram is basically the flow mean velocity as a function of distance from the wall. So basically, if we look at channel here, so we have this mean velocity profile, right? So what we are plotting here, basically the mean velocity as a function of distance from the wall. So the way we define it is that the zero point here. So 0 point here corresponds where the wall of the channel is, and as you move away from 0 point, you basically have higher velocity. And the bottommost profile we are looking at here is turbulent flow of a Newtonian fluid, turbulent flow, viscous turbulent flow. And the behavior here is well known here. So you can roughly divide that the behavior into a buffer layer behavior and a log layer behavior. So basically, what we are seeing here is that if you look at certain distance away from wall, you can see that the mean velocity will basically follow. Note that we have semi-log coordinates here. So mean velocity will basically, so this semi-log, so mean velocity will basically follow the logarithmic dependence. This is well-known von Karman log law, and it happens in all near-wall turbulence. And before you hit this layer, so-called log law layer, there's a transition layer that is often called buffer layer, right? And as you increase the polymer concentration, what happens? You can see that number one, the flow profile becomes higher. So that means that you are getting lower drag, higher mean flow, right? So if we take this case for example, what do we see here? That we still have a log law behavior here. We still have the log law behavior that has the exact same slope as the previous von Karman log law, but except that it happens at a higher distance. So the transition between buffer layer and log law layer is moved to a higher distance. And because of this this displacement, the overall profile becomes higher. So it becomes high. You have higher drag reduction. And for about 40 years, people think that's the whole story. All the drag happened in the buffer layer, nothing happened in the log law layer. That's the end of story. But the story has changed since the late 1990s. What people found is that once you have a very high level of polymer concentration, once your drag reduction becomes high enough, you no longer have the same behavior. You don't have the log law behavior anymore. You have this kind of profile. So you no longer preserve the same log law behavior as the von Karman log law. Rather, you just lose the von Karman log law altogether. So this is so-called high drag reduction or high level drag reduction HDR behavior, which is a very stark the difference from the low drag reduction or ALDR behavior. And for 20 years, a lot of people still believe that this is relatively qualitative behavior. People think that okay, once you have drag reduction that's about 30%, then you see the kind of behavior. And there's really nothing here. It's just how much. Well, this is just what you get when you have a high level drag reduction. And as we will show later, that we find that it's not story. It's actually there's a lot of non-trivial physics behind that. Another thing I want to draw attention to is the last two profiles we see here. You can see that the last two profiles we have here, they have very different polymer concentration, but still, so we can see that they have very different polymer concentration, but they seem to collapse onto the same profile. This is so-called a maximum drag reduction behavior. So basically, as you increase polymer concentration, you have a higher and higher flow rate, more and more drag reduction, lower and lower friction drag. But eventually, it will be bounded by an upper limit. And this upper limit, once you reach the upper limit, you can no longer push further. This is so-called MDR, maximum drag reduction behavior. And you can see the same behavior in a flow rate versus Reynolds number diagram. So, so typically, if you have a Newtonian turbulence, the flow rate depends on Reynolds number following this line. If you have viscoelastic fluids, you have a higher line because you have drag reduction, you have high flow rate. But eventually, you will be bounded by a same MDR asymptote. What is interesting here is you notice that for different polymers, whatever polymer you are using here, and in this diagram there are only two polymers, but this has been widely established that for a very wide range of polymers, you get the exact same asymptote. So this asymptote is very much universal to different polymer properties. So let's try to unpack what we have learned here. We know that there exists this MDR behavior, which by itself is very counterintuitive, because we know that the adding polymers can reduce the friction drag. That basically suggests that the polymers are making turbulence weaker. It's suppressing the turbulence, right? But the intuitive we think that if you add more and more polymers, you just make the, it's better and better at suppressing turbulence. Why doesn't it just kill turbulence altogether and give you back laminar flow? It doesn't happen. It gets just stuck somewhere in the middle. It never go back to laminar flow, but it just converts to a new type of turbulence. And this new type of turbulence, very counterintuitively, it is universal, regardless of what polymer you are using. And the reason it is counterintuitive is because this is highly viscoelastic fluid. We would think that the elastic property of polymer should have some say in its behavior, but it doesn't. And finally, the quantitative magnitude of this asymptote is given by the well-known work, so-called work asymptote. And any theory that we can ever come up with have to explain why that is stuck somewhere exactly at this point for the flow behavior. So because MDR has been this upper limit for reduction, and it is insensitive to different polymer properties for half a century. So I can almost say that for almost half a century since it has been discovered, the dominant thought in this area is that the flow convergent to the MDR indicates that the flow state has converged to some form of ultimate state, right? So for half a century, all the researchers have been looking for what is this ultimate state, so-called ultimate state of turbulence that is responsible for MDR. So basically, there's this happy place where all the polymer solution, polymer turbulence will go to, and once you get there, you are just stay there happily ever after. You never leave there. So that has been the dominant hypothesis out there, and I'll show again that our latest discovery will challenge this assumption as well. So let's just summarize a little bit about phenomenology. So if we, for fixed Reynolds number, and we increase the Weiss number, we make the fluid more and more elastic. And basically, there were a few stages will happen, right? Initially, when the Weiss number is low, we don't have any drag reduction, no drag reduction. And there will be an onset drag reduction level upon which we start to have drag reduction. That means that your flow rate becomes higher and higher. And eventually, it will converge to another upper limit called maximum drag reduction. And in this intermediate stage in which it is rising up, you also have two stages, that's so-called LDR and HDR, which is distinguished by at least the shape of the flow profile. And we can try to fill in the parameter space I laid out at the beginning. That's Reynolds number as a function of Weiss number in this space, right? So basically, if we look at the fixed Reynolds number and increase Weiss number, you can see that gradually you're sampling the no drag reduction, LDR, HDR, and MDR regimes. Note that the boundary for MDR here we have here is in dashed line because we don't know exactly what the boundary looks like. And so the research efforts in my group has been mostly focusing on the last two transitions. One is LDR to HDR transition, the other HDR to MDR transition. We haven't really looked too much into the onset of drag reduction behavior, which, by the way, there's still a lot of very interesting behavior happening over there. Maybe that's something that we'll leave for the future. And these two transitions are what I'm going to talk about today. So basically, as you make the flow fluid more and more elastic, the transition between different stages of behavior in turbulent flow. So we are, as George has introduced, we are a numerical computation group. So we use numerical simulation, direct numerical simulation. I do not plan to go into too much details about the simulation here, but we all know that the flow behavior, if you have a viscous fluid, the flow behavior is governed by the Navier-Stokes equation, which is basically the momentum and mass balance of the flow system. And from the Navier-Stokes equation, you will be solving for the velocity field and pressure field of the flow. And if you have viscous fluid, you just plug in Newton's law for viscosity. But if you have a polymer solution, if you have viscoelastic fluid, you basically need to have a new constitutive equation tell you how the fluid responds to the flow. That's so-called Fini-P equation. And I need this equation based on model polymer as dumbbells. That's two beads. That's connected by elastic spring. And we can capture the shape of dumbbell by so-called polymer conformation tensor. It's a tensor that we have to solve for, from which we know the stress field and from which we can basically couple that with the momentum balance. And if we try to non-dimensionalize the equation system, we'll end up with not only one Reynolds number, which was what we knew back in Newtonian turbulence, but now we have 4 non-dimensional groups, right? So the most important one that we have to remember here is, again, Weissenberg number. When the Weissenberg number is high, you're having stronger polymer effect, you're having stronger elastic effects, right? So let me just show you some videos that give you a little bit direct, intuitive view of what do we typically see in our simulation. So what are we looking here is this is this channel. The flow is moving in this direction, so from left to right, and the green tubes you are looking at are the vortices in the turbulent flow field. So not surprisingly, in a turbulent flow field, you have a lot of vortices that keep on evolving in time. They grow from the wall, they raise up, they break up, and then trigger new vortices, and the kind of cycle keeps on as the turbulence keeps on. So the image you're looking at, the video you're looking at here is for Newtonian turbulent flow. So you remember this picture. Now let me show you another picture, another video that is for polymer solution. So once you have a polymer solution, I assume everyone can see the new video here. Once you use a polymer solution, you can see that I still have vortices, but you can see that the vortices become a lot fewer and become a lot more scattered. So you can see that the polymers are making the turbulent vortices weaker, and that's part of the reason why we are seeing drag reduction behavior. So this is just to give you a very qualitative view of what's happening in turbulent flow from our simulation and comparing the Newtonian case versus the viscoelastic case. So let me just stop the video here, and I'll switch back to my slides. Now we look at our solution. We try to do a little bit more quantitative work. We can plot the same mean velocity profile I showed you before. The previous figure I showed you was an experimental figure. This one is from our numerical simulation. You can see that we capture the LDL behavior, we capture the HDL behavior, we also capture the MDL behavior. And another thing we noticed, we did here, though, so we are plotting the so-called Reynolds shear stress. If you don't start the turbulence, you only need to remember that this is basically a measure of how strong the turbulent motion is, how effective the turbulent flow is at reducing the mean flow and creating fluctuations in the velocity. So there's a very interesting behavior. So basically, as you increase the Weissenberg number, as the flow becomes more elastic, Reynolds shear stress will be lower because you are suppressing turbulent motion. But this kind of suppression is different between LDL behavior versus HDL behavior, right? So for LDL behavior, what you notice here, that the suppression happens mostly in this small region, that's a buffer layer. But there's really no suppression happening here. In the log-law layer, the LDL and the Newtonian turbulence have the exact same profile. But once you have HDL, you can see that the suppression happens across the entire channel, right? So they can resonate with our earlier observation that at LDL, your drag action happens in the buffer layer. At HDL, the drag action happens in both buffer layer and the log-law layer. So these are already some indication that there's something interesting happening here. Now let's just go a little bit deeper into this transition of LDL transition. What we are doing here, that we just decompose the shear stress into 3 components: viscous shear stress, that's basically Newtonian shear stress; Reynolds shear stress, you can remember that the turbulent shear stress, then polymer shear stress. And you don't really have to figure out what do they exactly mean. You only need to look at shape of the profile. You can see that in the buffer layer, as you have increasing drag action, you can see that you have a continuous change in all these 3 profiles, right? They basically change in a straight line, okay? But in the log-law layer, you have a sharp transition happening. So nothing very much happens at a low drag action, but you start to have just a new change at high drag action, right? You have a very sharp transition between the 2 kind of behavior. And so what we're seeing here is that the transition between LDL and HDL is not a simple quantitative effect of how much drag action you have, but it indicates a different mechanism of drag action. And the fact that you have this different mechanism, that basically means that there's at least 2. I say at least 2 because we now know that there are even more. There are at least 2 mechanisms of drag action that's happening here. The first one happens at an onset of drag action, which will start the LDL regime. The second one happens at the onset of HDL, which will trigger the LDL to HDL transition. This transition does not always happen at 30 or 35% of transition that like people believe. depending on what radius you're looking at, it may happen at a different level of transition, but it is a qualitative transition that will happen as you increase the Weissenberg number. So what is this new mechanism? So let's look at why polymer is good at reducing the turbulent friction. So we know. Again, we are talking about there are at least two mechanisms of stress reduction, right? So the first mechanism is well known. So basically, if you remember the video I just showed a few minutes ago, you have a lot of vortices in a turbulent flow. And typically, the vortices, they are aligned with each other, but they kind of rotate in opposite directions. So now in this schematic, the flow is moving into screen, right? So the flow is going into screen. We're looking at the cross section of the vortex here. Typical neighboring vortices are rotating in opposite directions. And what happens here is it will sweep up the polymers in the middle, bring it up. And once we reach here, you can see that the fluid is going two different ways. So this kind of flow motion will try to stretch the polymers. This is what we call extensional flow. The extensional flow is very good at stretching polymers, but polymer, as I mentioned before, it remembers its old configurations. It always try to pull back. So they're very strong polymer stress that try to pull things back. And this force, this stress that try to pull the polymer back is called to suppressive vortex motion. So what if we plot the intensity of vortices, which is measured by a quantity called Q? I'm not going into the details about how that is defined, but you just remember the Q measures how strong your vortex is. You can see that as you increase in drag reduction, the Q magnitude goes down, right, monotonically, right? So this is the first mechanism of drag reduction. But what triggers the LDR to HDR transition? We know that the LDR HDR transition should happen somewhere here, but we see a very small decline in Q magnitude. So the consistent decline in the Q magnitude, consistent suppression of vortex is not enough to explain why you have a second stage, the HDR stage. So now if you look at the vortex distribution in turbulent flow in different states, what you see here is that at LDR compared with Newton flow, the distribution is very similar. You have very strong high density vortices distributed in the flow field. Whereas at high Weissenberg number, once you reach HDR, you can see that this distribution become more sparse. You have this kind of empty pockets in which you don't have a vortex anymore, and you have these pockets in which the vortices are clustering up. So the distribution vortex becomes more clustered at HDR. So this is something that we first noticed as a distinction between LDR and HDR. So this is actually this is as much as for a lot of researchers, this is as much as they would go about concluding the physical message, because we have a turbulent flow, you have all kinds of vortex, they are being generated all the time, and they are all of different shapes. There are numerous of them, and it's impossible to keep track of them with a human hand. So what we want is can we be more conclusive? Can we come up with a way that we can more quantitatively and objectively tell us how many vortices do we have, what type of vortices do we have, where are the vortices, so that we have a more statistically meaningful conclusion that we can make about the vortex distribution and vortex dynamics, right? So the question we now have is that from directional numerical simulation, we can generate these images in which we have a lot of vortices. Can we tell a computer program how to automatically detect, count, and analyze vortices of different types? So we developed a method called a VATEP, vortex axis tracking by iterative propagation. The idea here is basically, so the dashed line we are drawing here is a vortex tube. So we basically, the idea here is that, okay, within a vortex tube, at the center of the vortex, you have strongest rotation. So the strongest vortex, the points which give you strongest vortex motion is at center. We can find those points. Then we come up with an algorithm in which we basically continuously connect these points together, right? So each time we're at one point, we look at where is the next point on my vortex axis line. So we come up with an algorithm that is very much similar to Pac-Man. You have this Pac-Man moving in space in a very smart way and try to connect these beads here. So once we connect them, what we end up having with is that each time we have a vortex, we can connect the line, the center line, the axis line of a vortex, right? So what we see here in the middle is, so we can find these kind of very complex vortex objects like this one. It has a very complex shape, and a vortex of this shape is so-called a hairpin. It's a hairpin vortex. Okay, I have overestimated how well I can. So it's a hairpin. I have overestimated how well I can write with my mouse here. But again, I'll type it later. You'll see a typed version. It's a so-called hairpin vortex that is very, very well known that is of special importance in air turbulence. But another type of vortex you will see is these kind of ones, right? The green one here is most linear. It's called a streamline vortex. So we can capture all different types of vortex, and from there we can basically go into a direct numerical simulation data. We can look at each individual vortices, and we can analyze what are their shape and what is their position, etc. So we apply this weighted algorithm into Newtonian turbulence and LDL and HDL cases, and you can clearly already see some difference here, right? So in the Newtonian turbulence, you have streamline vortex for sure, but you also have this kind of hairpin vortex, right? At HDR, you can still find this hairpin vortex. It's a clear hairpin, right? But you also have a linear streamline vortex. But at LDR, you don't see so many of these hairpins anymore. Most of them are very elongated streamline vortices. You can already see those differences, right? So what are the significance of these two types of vortices? So we go back to the literature and we look at, okay, why the turbulence sustains itself. So basically, each time we have a vortex, how does the vortex dynamics make sure that once one vortex dies down, there will be new vortex being triggered up? And these are called, vortex regeneration cycles, right? These are called vortex regeneration cycles. So this is a highly simplified view. We classify them into two classes. One is so-called street instability cycle. The other is the parent offspring cycle. The street instability cycle means that we start with stream of vortex. The downstream side of vortex will go up, which is called a lift up process. And once it goes up, there will be a lot of turbulent fluctuations once we move away from the wall. So turbulent fluctuation will try to swing the vortex sideways. Once it is swinged sideways, you form this kind of hairpin. The hairpin will keep on growing, but it is unstable. Eventually, it will break up into pieces. And these kind of pieces will trigger, cause the disturbance that will trigger the new vortex being grown. The parent offspring cycle basically means that if you have a vortex and it doesn't lift up, but still you have this kind of a rotation vortex will create a very strong shear layer between the vortex and the wall. And this shear layer, the instability of this shear layer will create another vortex immediate upstream or downstream. And it basically can create a new vortex that is next to the old one. So you can see the difference between these two is that in the first mechanism here, it is non-local. That means that the new vortex does not have to be generated right next to the old one. Whereas in the second mechanism, the parent offspring mechanism, it is localized. The new vortex is always generated next to the first one. And in both mechanisms, you have a streamline vortices, right? But only in the first mechanism, you will generate hairpin vortices. So this is just to give you a little overview of about what theory are there about vortex regeneration. Now we go back to our data. We think, okay, if we have a vortex, I can measure what's its minimum position, wall position, or its maximum position. So if these two positions are similar, that means that the vortex is lying flat, right? So if these two, so I can plot the minimum position versus so this maximum position versus the minimum position. I can plot these two, and if these two are similar, that means that you are being drawing the distribution will fall along this diagonal line. That basically means that your vortex is lying flat. But if the maximum position is much higher than the minimum position, that means that the vortex is lifting up, right? Like this one, Y max is much higher than Y minimum. So it's lifting up, and that means that you are looking at this span. What we're seeing here is that if you look at streamline vortex, in Newtonian flow, you have both these lift up and flat vortices. But at HDR, you can see that we still have this kind of flat vortices, but you don't have this lift up vortices anymore. So having high elasticity is suppressing the occurrence of these lift-up vortices. Now, if we look at hairpin vortices, we do the same thing. What we find here is that there's no such thing as a flat hairpin vortices at all. All hairpins are lift up. They are all at this span, right? But the span becomes weaker and weaker, right? So they only come as a result of lift up. So let's summarize what we have here. The physical picture we have here is that if you have Newtonian LDL flow, if you're a Newtonian flow, you basically have this kind of self-sustaining mechanism in which you can generate a vortex. The vortex will grow, and eventually you can see that it will grow into a hairpin, right? It grows into a hairpin. The hairpin will break up, and it will trigger a new vortex somewhere. And LDR, what LDR does is that LDR makes all the vortices weaker in general. There's a cross-board weakening of vortices, but again, it still largely follows the same mechanism. But at HDR, what happens is that the HDR will prevent the vortex from lifting up. So it will prevent the generation of the hairpin vortices. But instead, the mechanism will be dominated by the parent offspring mechanism. This mechanism by nature is localized. That's why in HDR you see localized vortex pockets, clusters. So at this point, we think that we have a very good understanding about the transition between LDR and HDR, right? So let's take a little bit bigger picture here. So what I'm showing here is the friction, turbulent friction as function of Weiss number. So we can see that, okay, we capture the initial node gyration. We have a unstable gyration go to LDR. We capture the LDR to HDR transition. So, and then eventually there's MDR. At MDR, you can see the friction become constant, right? So we capture all the behavior. So we think that we have very good understanding of this transition here, LDR to HDR transition, until we look at whatever is happening at this point at about Weiss number is 40. The friction suddenly drops into very low magnitude, then it comes back. What happens here is that the flow becomes laminar, then becomes turbulent again. So within HDR, you can see you have two windows. You have one window of turbulence here, it becomes laminar, then you have second window of turbulence here. This phenomena reminds us of a very interesting phenomena reported by your own Professor Shori a few years ago in his experiments. So if you look at his experimental pipe flow data, for fixed Reynolds number, if you have low Reynolds number, when you increase polymer concentration, you start with a turbulent flow, become laminar, then you have another stage of turbulent flow. So the fact that you have two different stages of turbulent flow basically suggests that you have two different kinds of mechanisms that give you turbulence, right? So far, everything we have been talking about falls in the first type of turbulence, including both LDR and this part of the HDR we have talked about. They all fall into first type turbulence. There's very little we know about second turbulence, right? Second type of turbulence. Okay, so let's just take a look at what are the two types of turbulence. The first type of turbulence is something that we know a lot about. It's something that we would learn from any turbulence or fluid mechanics textbook. Now I call it inertia-driven turbulence because in this type of turbulence, the flow instability is sustained by the fluid inertia. And once you introduce elasticity by the polymers, elasticity will make the turbulence weaker. It will suppress turbulence and cause gyration. And the flow structure is very clearly that most of the vortices will align in the flow direction. It will be streamwise vortices, right? Remember that in this diagram, the flow goes in this direction. Okay, so it will be streamwise vortices. The second type turbulence is something that is known a lot more recently, and Professor Shori has done a lot of excellent experimental work in that as well. It's so-called elasto-inertial turbulence. So in this limit, we still believe that inertia actually is partially driving turbulence. It is still driving turbulence, but elasticity also plays an important role to drive the turbulence. It's no longer only suppressing turbulence, driving the turbulence as well. Both of them are making turbulence stronger. And this kind of turbulence structure gives you span-wise turbulence. So note that in this diagram, the flow goes in this direction, whereas your vortex goes sideways. Okay, so comparing the two, you can see that it's very easy to distinguish the two types of behaviors, right? So because of this kind of finding, so the dominant hypothesis in the field is that the reason you have a maximum gyration is because of this so-called EIT. This EIT is a 2D flow state in which you have span-wise vortex, and as you increase Weiss number, EIT becomes more and more important, whereas the IDT, the streamwise vortex, become more and more suppressed by polymers. So eventually, you will totally kill the IDT streamwise vortex. You're only left with EIT, and this pure two-dimensional EIT flow state is your MDR. So that has been the leading hypothesis in the flow field. But there's a very important question about the hypothesis. If this is the EIT state, this elastic instability state is MDR, why is it insensitive to different polymer solutions? It's very hard to believe, because if elasticity, polymer plays such an important role in sustaining turbulence, why it is not sensitive? It does not reflect in the mean flow. So we have some doubts about this hypothesis. That's why we conduct this test. First of all, we find the EIT solutions in a 2D flow. So yeah, if you say that the MDR is 2D limit of EIT, let's just look at the 2D limit of EIT. Let's look at whether that looks like MDR or not. So what we are seeing here, that if we have 2D EIT, again, we look at the friction, flow friction, turbulent friction as a function of Reynolds number or Weiss number as you increase Weiss number. What we are seeing here is that as you increase Weiss number, you have higher and higher friction. So the friction doesn't, first friction doesn't reduce. Second, friction doesn't converge to any plateau that the MDR should give you, right? We never get MDR behavior in a 2D flow. And if I repeat my simulation with a different polymer molecular weight, if I make a longer weight, experiments tell me that at MDR, you should get the same flow, same mean flow, but we are getting different mean flow. So we can conclude now that the 2D version of EIT, it never gives you convergent friction drag. It never gives you MDR behavior. MDR cannot be this 2D version of drag reduction. In order to have drag reduction, you have to have 3D flow. So if you do simulation in 3D flow, this is what we found. You can see that you have drag reduction, eventually converge into plateau. You have this MDR behavior. You only have MDR behavior in 3D flow. So the simple 2D EIT answer is not sufficient to explain why we have MDR. So we can look a little deeper into what happens in the dynamics in the 3D flow, right? So this is one sample equals 40 solution, and right now we're basically looking at how the thermodynamics change in time. We draw the trajectory into this space. So in space, we have a few solution objects. This is called active turbulence. This is basically the turbulence state that is most important when you have Newtonian flow. This one is so-called H state. Is at a laminar turbulent boundary. This is what is more important as you reduce the Newtonian turbulence. So you will push you towards this state, and we used to call this hibernating turbulence. And the EIT is here at this corner. So we just look at how this is balanced. This triangle relationship between these three states is influencing the overall dynamics turbulence. So at low to moderate Weiss number, you have these kind of cycles. So it's between active turbulence and H state. So this is what we call type A cycle. And type A cycle is basically IDT, inertial driven turbulence. But when your Weiss number is high enough, type A cycle is no longer enough to keep your turbulence sustained. What will happen is that you can no longer keep turbulence sustained. So at one point you will get laminar flow. But once you have even higher Weiss number, you start to give rise to this new EIT state, and this new EIT state allows you to form another kind of orbit. This is called type B cycle. This is type B cycle. Notice that you have to have EIT to have this type B cycle. Otherwise you will just go back to laminar flow. And as you further increase Weiss number, so at very high Weiss number, what you can see that so this is where type B cycle, and you can see that even type B cycle becomes irrelevant. You end up with another cycle called type C cycle. This type C cycle. So we can see at least 2-3 different types of cycles here. And these are time series, and we can see this behavior of these time series as well. You can ignore these more detailed annotations here, but basically the type A cycle are these kind of dips here you're looking at here, right? And type B cycle are these kind of much longer dips. Okay, we know these are type B cycles because if you look at this part, the elastic energy is the rate of turbulent energy conversion from elastic energy to turbulent energy is positive. That means that elasticity is feeding into turbulence. Then for type C cycle, what you see is the entire different kind of fluctuation. It's quasi-periodic. It happens at a much higher frequency. So these three distinct type of cycles happening here. Now let's look at again, go back to the overall picture of a so-called multi-stage transition in turbulence. Again, for same Reynolds number, we look at what happens when we increase Weiss number. The top row here is what happens in the phenomenology, what happens in the flow measurement. So these are things that you can see experiment. We know that you have a no reduction, LDR, HDR, and MDR. The bottom column is what we think is happening in the underlying dynamics. This is what happened in underlying dynamics. So MDR, no drag section, LDR, and the first part of HDR belongs to type A cycle, right? So the initial vortex lift separation all happening here. Then after that, we have a lambda window. Then we have another stage of HDR. So notice that what people think HDR is not even one stage. This is two distinct stages of dynamics here. And that's where type B cycle becomes important. And type B cycle continues to dominate until well into MDR. Then you have type C cycle. And once even reach here, what do you see here? If you look at the time correlation function of the type C cycle, an increase-wise number, it doesn't really converge. You have higher and higher fluctuation and longer periods. So even type C cycle keeps on increasing with wise number. So remember that earlier I mentioned that the dominant hypothesis was that at MDR you converge to some of ultimate state, which is no longer changing with wise number. What we see here that at MDR you don't have one single ultimate state. You have very different dynamics. You have both type B cycle and type C cycle dynamics, and even the type C cycle dynamics continues to change, even though that the apparent mean flow is not changing in MDR. So MDR is not in one flow state. It is still constantly changing a group of flow state that is constantly changing with the level of viscoelasticity. And by that, I would conclude that the reason why we, after half a century, we were still not able to explain MDR is maybe because we have been looking at the wrong direction. We shouldn't be always looking for ultimate state that doesn't exist. Right. So this is the key conclusion. The dynamics continues to evolve with Weisenberg, even after your flow has converged to MDR. So I'll skip these more detailed description of these cycles because I think I've already covered the most important message here. So just give you a little summary. Our focus is in viscoelastic turbulence. Once we look at the increase in Weiss number, the rich behavior, rich dynamics that happens as you increase Weiss number, as you make the fluid more and more elastic. We know that phenomenologically we have a dry adhesion behavior changing from no dry adhesion to LDR to HDR to MDR. What we have uncovered here is that the underlying dynamics change from type A cycle to type B cycle to type C cycle. And from this picture, we can already explain the LDR to HDR transition. But we also opened a new can of worms that there's a lot of things that we didn't realize before. There are actually two different HDR stages. We still don't quite understand the second HDR stage, and we don't really quite understand MDRs, right? So as mentioned, we understand the reason for the first HDR stage, but we don't understand what happens in the second HDR stage. And eventually for MDR, we basically find that the old assumption no longer works. We don't have a single ultimate state about MDR anymore. And what we call EIT, we may still consider MDR to be more or less relevant to EIT. But we should re-examine what do we mean by EIT. It is not even one kind of flow state. EIT can be considered to be a very general umbrella term that covers a group of different behavior that includes both our type B and type C cycles. And we don't really fully understand that. We don't really know why that gives rise to MDR behavior. So in conclusion, I just want to make sure that the credit is given to where it is due. All the work here were done by a highly talented and productive PhD student, Lu Zhu, who is now doing postdoc at Cambridge. And obviously, we thank all the founders and people who provide us with a computer. And again, thank you everyone for your attention. And I would like to thank again the department for the invitation. So hopefully we have a few minutes to answer your questions.
Thank you very much. Very interesting. I learned new things about the Weisenberg number and its correlation with the Reynolds number. So questions for the speaker. George, would you like to take over?
Sure, I could do that. I guess maybe I can start off with a question just to kind of, I don't know, put the first tip in the pot to get the questions going. Excellent talk. Thank you so much, Dr. Shi. I really appreciate it. And obviously there's a lot more we're learning day by day. So a lot of what you presented today is what I would consider on the cutting edge of the research in this field. So thank you for coming and presenting this. I have some, the biggest conclusion that I saw from here is that, in fact, MDR is not in ultimate state. There's things are still evolving. Structures possibly are still evolving. Did I miss it, or can we? Perhaps you hinted on this. Can we understand why the friction factor is constant at MDR, despite the evolution of the state?
Yeah, you're spot on here. Yes, that's our key conclusion, that when we talk about MDR, it is not a single state. Things are keep on changing. We have very limited understanding of why the friction is keeping constant. That is still an open question. I think what we know now is that when we look at MDR, it's basically but first of all, the flow is not convergent, and that shouldn't be surprising once we realize that EIT plays an important role, because like all kinds of elastic instability, it should be sensitive to polymer solution, polymer properties. When you increase Weiss number, when you increase concentration, all kinds of elastic instability will keep on changing as you change these parameters. But it just so happens that when the turbulence is changing, when the instability is changing, as we change the Weiss number, as we change the polymer concentration, it's not reflecting in the mean flow. So it's not reflecting in the mean flow. It's more reflecting some of fluctuating properties, which has not been looked into too much details in the past. So one way we can look at it is that, for example, if you can look at these two cases, Weiss number with 64 and Weiss number 400. So both of them belong to the MDR according to our all simulation. But the first one is type B cycle, the second one is type C cycle. You can see that the characteristics of the fluctuation are very different. For the first one, we have the kind of strong spikes separated by a very smooth period in your friction factor. And second one, you have the kind of small wiggles, right? And both of them give you the same average friction, right? So if you compare this friction, first for this friction, if you do a time average, you see almost the same. At least within the experimental statistical uncertainty, you see almost the same friction level. But it's but basically what's hidden behind that is characteristics of the fluctuation. And that's the key of understanding why. So basically understanding why all these different flow states, they just choose to converge at this friction level is key to understand MDR. I know I didn't answer your question, but that's as much as we know at this point.
All right, thank you. That's fine. I've always looked at the experimental results of MDR, and everybody agrees that things are constant. But I mean, if you just look at it, there's actually a lot of spread there. So is it possible that, in fact, we're not reaching a constant, which is MDR, but we have a narrow spread around the region, I guess? Is that a possibility?
That could certainly be the possibility.
Okay, thank you. All right, perfect. Thank you. Any other questions for Dr. Shi?
I see a question from Behrad. So he's thanking you for the great presentation. I think there would have been a limit to the amount of polymer that can be added to the flow. Does that mean that in even in the maximum case, the MDR state is still evolving?
Right. So let me make sure that let me try to answer this question, because I'm not sure if I totally understand the question. So if my answer doesn't answer the question, feel free to jump in here. So I answer it in two parts. Number one, yes, there's a limit about how much polymer you can add. And obviously, if you have too much polymer, and we all have experience, the flow will become very gooey and highly viscous, and you can't really have turbulence at all, right? And everything we have been talking about so far, and you know, I live in a theoretical world that I'm allowed to do that in my model, is that we still consider polymer solution to be dilute, right? So we add polymer to the extent that it is still dilute. And if you choose the parameters carefully, it is possible to reach MDR when the polymer is diluted. Once it's no longer diluted, there are a lot of other things that will happen. Will change the entire narrative we have so far. The viscous become higher, and also the fluid becomes shear thinning, which we don't even consider so far in this framework. But everything we have reported so far can be discovered in experiments in highly dilute setting, which Professor Shori is very good at doing experiments as well. So we can repeat all these discoveries in dilute solution in experiments as well. So the limit of how much polymer we can add is basically limited by this upper boundary. It has to be dilute. And what we found is that in this dilute regime, you either add, and you can make a fluid more elastic by adding more polymers, which is the easiest thing to do in experiment. Or you can make it more elastic by using polymers that's more flexible, has more flexible backbone, or has higher molecular weight. You can change these parameters to make it more elastic. And as you make it more elastic, you are hitting the MDR behavior. And what we found here is that once you hit the MDR, either the mean flow is not changing, or as Dr. Shori just mentioned, it may be changing with some small variation, but it's so hard to detect. And so people didn't realize. So basically, mean flow becomes no longer sensitive to how elastic the fluid is. But what we found is the underlying dynamics here, the fluctuation characteristic here is keep on evolving. I'm not sure if that addresses your question, but feel free to follow up if there's anything that doesn't make sense to you.
Thank you. And Behrad, I can unmute you if you cannot unmute yourself, if you want to basically speak, but please feel free to iterate within the chat box or ask me to unmute. Okay, let me see. Okay, I think I unmuted you as well. Okay. While we're waiting for that, any other questions, comments? George, do you see anything that I might have missed? No, I think, okay, Behrad is basically saying that's clear and answered his question. I am going to check Q&A here.
So while we wait if there's any more questions, I think one of the more difficult things to understand from people who just started doing their their graduate studies is this plots in, if you're not doing numerical simulation work, these plots in wall units, so the Y plus versus U plus.
Yeah.
So is maybe if we can clarify just basically what this is. I mean, is this just basically what the flow profile looks like, and what is the connection with friction factor? Could we elaborate a little bit on that, Dr. Shi?
Yeah. So this is something that I was trying to hide under the COVID, because it's not only difficult for people on the experimental side, it's difficult for everyone who studies turbulence. So part of it is because turbulence is a field that has been studied for hundreds of years, and there's so much established terminology that has been here. And basically, a new graduate student has to spend a lot of time to kind of find their way across all the terminology. So what George was referring to, so I have highlighted everything here, so it's a little hard to see. So let me just go to the other plot here. So you can see that I have this little plus sign in my velocity and length units here. So what basically happening, what basically we are doing here is that we know that in fluid mechanics and fluid dynamics are notorious for trying to non-dimensionalize everything we do, right? So if you have a channel flow, it is very common that typically here I have a channel here. So if a channel flow, it is very common that we will non-dimensional velocity by less than mean velocity. We didn't use mean velocity, but again, more commonly in experiment, you'll be using mean velocity to non-dimensional all the velocity in your system. You'll be using the diameter of the pipe or the height of the channel to non-dimensional all the length unit. And if you non-dimensional equation system, that's how you end up with having a Reynolds number in your equation. That's thing that you should have learned from undergraduate fluid mechanics, right? And then we call this non-dimensionalization so-called outer units. But in turbulence, what happens is that is that if you look at turbulent physics, first of all, in turbulence, a lot of interesting physics happens here. Happens in the near wall part. That is very close in this near wall part. And when you're happening here, when you look at the vortex generation or the vortex dynamics in this near wall layer, it doesn't really, when you when you look at physics, when you look at population of all the players in this layer, the other wall is just too far away. It doesn't really feel the influence of the other wall, right? So how high, the overall height of the channel here is irrelevant. It is irrelevant here. Sorry, that's it. Okay, I think I'm messing up, but you get the idea. You see, how high the overall height is irrelevant here. What matters here is how high your boundary layer is. This is a length scale that matters to you, right? Similarly, for the physics in this small region here, the mean flow of the overall pipe, overall channel is no longer relevant here. What happens is the velocity in a new layer. So if you try to rescale the velocity and length using units in this layer, we call that inner units, or we use a little plus. So whenever we are showing our results in inner units, we'll show that with a little plus. And to show the success of this approach, the biggest evidence is just the biggest evidence of the success of this approach is just the von Neumann law I was talking about, right? So you have this von Neumann law. So basically, if you have a Newtonian turbulent flow for different Reynolds number, if you have different Reynolds number, if you scale everything outer unit, if you use the channel height, if you use the overall mean flow, you'll get a different flow rate. But if you scale that in inner units, if you scale that in the less scale that corresponds to boundary layer, in velocity that corresponds to the near wall velocity, then everything will collapse onto the same profile for different Reynolds number. That just shows you that these scales, length scale, inner scale, these inner velocity scale, these inner length scale are the relevant scales for the turbulent behaviors in near wall turbulence, which is where the drags are being generated. So I think there's another question in the chat.
There are a couple of questions. So Ahmed is asking, there was a connectivity error around 154. I reset the device and back online. That's a comment, I guess. So the question is, Homa is asking a question. Thank you for your great presentation. How did you estimate relaxation time of the Weisenberg number for your simulation?
That's a great question. The answer is that we didn't really. So far, what we are doing here, and as well as everyone who is doing simulation work, is that we are not really mapping our system to any real polymer. Meaning that when I say Weisenberg is 400, I didn't really map that into a specific polymer, let's say polyethylene oxide of a certain molecular weight. We haven't done this. Mapping. But what we have done here is that we just use Weisenberg number as a parameter that we can change, and we look at how things change as we increase Weisenberg number, right? So in that sense, when we compare our results with experiments, we cannot draw direct quantitative comparison. We cannot say that our simulation mapped to this particular experiment point to point. But what we can say is that as we increase Weisenberg number, we will see these kind of behaviors, this series of behaviors. And in experiments, as you increase Weisenberg number or you increase the point concentration, you will see a same series of behavior. So in terms of the transitions, qualitative transitions, we can capture that, but we can not do the quantitative mapping between experiment and simulation. That being said, there has been some recent efforts of trying to connect the two words, trying to connect the relaxation time in simulation with something that you can measure in experiment. And most of efforts that I have seen focus on measuring the extension of rheology of fluid, and from the extent, if you measure the extension of rheology of fluid from the extension of rheological property of the polymer fluid, you can estimate a relaxation time. So you can get some sort of connection between the two. But again, so far I haven't seen any direct agreement between experiment and simulations in that sense, partially because in simulations, the Weiss number we have here is very well defined. We use a very simple, if you recall, we use a very simple dumbbell model, right? So our polymer only have 2 beads and 1 spring. Let me just switch to our polymer only have 2 beads and 1 spring, and it only have 1 relaxation time. But in real experiments, the relaxation time is not one single relaxation time you are dealing with. You have a spectrum of relaxation time, and the number you get depends on what kind of measurement you are getting. So in that sense, it's very it's not easy to draw direct quantitative connection between these two.
Okay, thank you. And I guess Thomas thanking you as well.
Thank you.
George, do you see anything else?
I don't see any other questions coming in. And thank you so much for the explanation as well for the wall units or inner units. That's always something that is difficult to explain, and so I'm sorry I used you as.
No, well, I have to do that to every incoming graduate student. So
yeah, all right, thank you. Some presentation. Have a nice day as well. Okay, so I don't see any other questions.
All right. Yes. So I guess that can conclude our seminar for today. I'd like to thank you again, Dr. G, for this great presentation. Looking forward to interact with you further. Hopefully, have you here in person at some point. Not that far of a drive, right? Probably 3-4 hours from Hamilton.
Yes.
Yeah. Okay, wonderful. All right, thank you very much again.
Thank you very much.
Have a nice weekend.
Thank you very much. Thank you, everyone. Nice meeting everyone.
Thank you. Thank you.
I'll stop sharing.